I'm going to talk about bandwidth. And actually, just to be really old-fashioned about this, it's a 60 symbols video, and it's got a symbol, which would be delta F, because it's a range of frequencies, is essentially what bandwidth is. It is related to the amount of information you can get down a fibre, so you know the bandwidth of your broadband is telling you how much information you're actually getting. There it's largely limited by how much you're prepared to pay your broadband company, but there's a sort of fundamental physics limit as to how much information you can actually get down, say, a piece of fibre optic cable. You can apply this concept to anything, to sounds, to radio waves, to light down an optical fibre, whatever you like, but the idea is the same, which is that essentially light, sound, whatever, comes in waves, right? And the classic sound wave or light wave is a sine wave. I have a little app here which will produce a tone. There we go. There we go. That's a sine wave. And there's no information content in there at all, right? You can't use that to actually transmit information. If you actually want to convey information, in particular if you want to convey digital information, you need ones and zeros. And that essentially means you need pulses. You can't do it with just a sine wave like that. You need a little, you know, a beep, then nothing, then beep, then nothing. You need to break it up into pulses. And you can't do that with a single frequency, because a single frequency always sounds like that. Right? It's just a single tone.
Professor, couldn't you turn it on and off?
I could turn it on and off, but actually then it wouldn't be a single frequency anymore. Let's back up a little bit. Okay, let's do something a little bit more sophisticated, which is, so there is my tone, and I've got Brady's iPhone here. My phone is tuned to produce a tone of a kilohertz, 1000 hertz, and I've set Brady's up to produce a tone of 1001 hertz. Okay, so you know we can play Brady's. That's what 1001 hertz sounds like. And that's what 1000 hertz sounds like. Really very similar, not very much to tell between them. The interesting thing that happens is if we play them both at once. And if you listen carefully, you can hear that there's this strange beating effect, that it's sometimes louder, sometimes quieter. But one way might make it clear is if I change the frequency a bit, you'll hear that the beat change. So if I take Brady's phone from 1001 hertz to 1002, you'll hear that the beats get quicker. So let's turn off the annoying noises for a moment.
Please.
So, physically what's happening is you've got these two waves of slightly different frequencies. And that means they're just kind of over time drifting in and out of phase with each other. And when they're in phase, the waves all add up and you get a louder sound. And when they're out of phase, the waves cancel each other out and then it goes quieter again. So you get these beats of loud and quiet. And what I really want is I just want one of those beats. I don't want a whole series of them. I want kind of one blip. And I can't quite do that with only two frequencies, right? I've only got two frequencies here. But if I had lots of frequencies, then actually I can produce a single beep, a single blip. Okay, that's not, because then basically everything adds up incoherently at one point, so you end up with lots of sound there, but then it destructively interferes everywhere else. So I can produce a single little pulse of beep, and that's really what I want to do. If I'm going to convey information digitally, I want to send a whole string of these beeps. But in order to do that, I needed to combine different frequencies together, right? It wasn't just one frequency, it was a whole range of frequencies. And there's this very simple relationship between the range of frequencies I add up and how short the beep is. And essentially, so let me write this one down. So essentially, if I've got a range of frequencies, delta F, and I'll produce pulses, duration delta T, so the bleeps I end up producing, the product of the two always comes out to be approximately equal to 1. And so you see, if I want to produce very short pulses, so if I want to produce, if I want to pack a lot of information in a finite period of time, I want to produce very short pulses, so I can produce, a whole load of code in a very short period of time. So you can see from this formula, if I want delta T to be small, and the product of delta F and delta T has to be 1, as this term gets smaller, the only way I can do that is by making this term bigger. In other words, to make shorter and shorter pulses of sound, or light, or whatever it is, I need a wider and wider range of frequencies to do it. And the fundamental limit to putting information down a fibre optic cable is what range of frequencies can I put down. Because although a fibre optic cable, it'll probably let blue light go through and red light go through, it won't let X-rays through or radio waves through. It's just not, optical fibres don't work that way. And so there's a finite range of frequencies, a bandwidth of light that I can put down a fibre optic cable, and that fundamentally limits how short a beep I can send down, how short a blip of light I can send down. and that's what limits the amount of information you can put down a fibre optic cable.
So, Professor, when I'm using the internet and I get a 1, is that what's happening to create the 1? They're interfering all these different colours of light, except a certain one to...
So if some of the path between you and whatever server it is that you got that 1 from is down a fibre optic cable, that's exactly what's happening. A little blip of light has been sent down that fibre optic cable to represent the 1. And to produce a little blip of light, you need a whole range of frequencies of light to do it. It's not just a single colour.
They can't just switch something on and off,
but
like Morse code.
Okay, so that's the weird thing, right? Even if you've got, supposing, so everyone thinks like a laser produces light of a single colour, okay? Single wavelength, single frequency. Actually, that's only true if you leave it on forever. If you leave it on forever, so you're not switching, then you do indeed have a sine wave that goes on forever. And that is indeed strictly a single frequency. As soon as you switch it on and off over some finite period, it's no longer a single frequency. So even a laser, so let me, again, maybe a picture will help with this, right? If I've got my light, my light wave that goes on and on forever, that really is, if I were competent at drawing, a single frequency, a single wavelength of light. If, however, I just switch it on for a little while, so it's off, then I've got a pulse of light, and then it's off again. Okay. This no longer has a single wavelength associated with it. It looks like it because you can see, well, it's going up and it's going down. But actually to produce something like this is clearly different from this. And to go from having a real single wave to having this, I've got to add a whole bunch of waves together of slightly different frequencies to produce something like this. And so this is actually the superposition of a whole bunch of slightly different frequencies. Even a laser, which you think of as, well, it's a single wavelength of light, if you switch it on and switch it off again, you've actually produced a pulse of light that has by its nature to contain more than one frequency. If I have a laser, I can just switch it on and off, right? I don't have to do anything clever. I'm not saying, oh, I'm producing a little bit of this red light and then this little bit that's a bit bluer and this little bit that's a bit redder in order to make a pulse, right? Nature does all that for you. That actually by switching it on and off, the laser, instead of producing this single wavelength of light, is actually producing the right superposition of wavelengths of light to make a pulse.
So there aren't a bunch of engineers and experts that had to come up with a way to make all these things interfere and...
No. It's all done, nature that takes care of it, that just by switching the thing on and off at the right wavelength, at the frequency you want to switch things on and off at, so at the, producing pulses, that by its nature produces light which is no longer a single wavelength. But it turns out that actually there's a quantum mechanical application of all this as well, right? And one of the things that people know about quantum mechanics is this wonderful thing called the uncertainty principle that says there are various things that you can't measure at the same time. So you can't measure the position of a particle and its momentum at the same time. And one of the other forms of the uncertainty principle is that you can't measure the time when something arrives and its energy at exactly the same time. So if you measure the energy of something and the time of arrival, then there's an uncertainty. You can trade them off against each other. You can measure times very accurately, and then you get rubbish measurements of energy, and vice versa. And it turns out this is a simple example of exactly that. And the reason is, if we go back to this equation again for a second, that the frequency here, instead of thinking in terms of these pulses of light and the classical picture of waves, think about photons and when a photon arrives. If we've got a pulse of light like that, we know that the light has to arrive sometime within this time. So the photon we detect is going to arrive within some finite time or other. And so because of this relationship up here, because it's some finite time of arrival, that means there's also a finite range of frequencies that photon can have, what the frequency that we actually measure for the photon. And in terms of frequencies of light, there's a very simple formula that says that the energy of a photon is related to its frequency by this relation, Planck's law, right? That the energy of the photon is Planck's constant times the frequency of the light. So an uncertainty in the frequency of the light then translates into an uncertainty in the energy of the photon. We have this trade-off, right? We can either measure the energy of the photon arrival very accurately, but because of this uncertainty relation, that means that we can't predict exactly when it's going to arrive, so we don't know what time of arrival will be. Or alternatively, we can very tightly force a photon to arrive at a particular time by saying, well, we'll switch the laser on and off very quickly, which means we know exactly when the photon took off, which means we know exactly when it's going to arrive. So we know when it's going to arrive, but because it was then a very short pulse, that means there's a very large range of frequencies in that pulse, which means the energy we record for the photon is very large. And so there's this trade-off, this uncertainty relation that says that you can't measure these two properties of a photon or indeed any particle simultaneously. You can't measure both its energy and its time of arrival very accurately. The ultimate limit for how much information you can squeeze down a fibre optic cable is set by exactly this, because you might think, well, I can just keep pushing my, if I want to pack more information down, well, I just make my pulses shorter and I can send them through quicker that way. But actually, as each time you make the pulse shorter, the range of frequencies of the light in that pulse get wider, and eventually you're going to reach a point where some of those frequencies are the kind of light that won't go down the fibre optic cable anymore. So this really is, from an engineering point of view, this is the fundamental limit as how much information you can squeeze down a piece of fibre optic cable is set by this relationship.
And what is the limit? What's the shortest pulse?
I'd have to look it up. I've got the calculation. If you want to know, I can tell you. Which lecture? That one maybe. It's a few femtoseconds, a few times 10 to the minus 15. So this means if you've got a fibre optic cable that just works in the optical part of the spectrum, so just in terms of rough numbers that works from kind of blue light to red light, it turns out that the shortest pulse you can send down that is about a femtosecond. So that's 10 to 0.15, 14 zeros 1, so 10 to the minus 15. So that's the shortest pulse that you can actually send down that, and that pulse actually contains light all the way from the red to the blue end of the spectrum. If you try and make your pulse any smaller, the range of frequencies will push you out of the optical part of the spectrum.
So you could get zeros where you were going for a 1.
So you could, your pulse would fall apart. You can't make a nice neat pulse anymore because some of the frequencies you need to make that very neat pulse won't actually travel down the fibre at all, and it'll all get horribly messed up. In terms of data transfer, that basically, I think it works out, you could send, the ultimate limit is you could send about a terabyte of data down a fibre like that in a few hundredths of a second.